All right, mic check. Just doing a test. If people watching on YouTube or LinkedIn can just send a message that they can hear everything clearly, that's fantastic.
Okay, testing. Can you hear me?
Yeah, we can hear you perfectly.
Yep, and it's clear there as well.
We can hear. All right. Sounds good.
There's like a get together going on with a couple of kids where they've in the living room with a bunch of them, so that's why you're hearing a few of them.
They're in Oxford with you.
Welcome. No, they're in London.
Welcome.
Yeah.
Okay, welcome, guys.
All right.
So let me yeah, I'm ready when you are.
Wasim, are we live? Usman, are we live?
Yeah, we're right. We're live.
Perfect, Jim. We can start, I believe.
All right, fantastic. Thanks so much for coming to the Dome. Right now, we're wandering around in the galaxy, and we're going to be talking about astrobiology. The key in this, of course, is really understanding what is astrobiology. This is one of several courses. The classes are given here, from an introduction to astrobiology to life on Earth over time, telling everyone how we're doing in our search for life in several locations. The class 3 talks about the search for life on Mars. Class 4 is all about ocean worlds in the outer solar system and the possibility that they could have life. And then finally, we'll end the week with the search for exoplanets. So this is a fantastic overview of a very brand new science area. Astrobiology by NASA began the process of looking for life beyond Earth. Hi, I'm your instructor, Jim Green, military scientist. I've retired from NASA. I've held a number of positions from the Director of Planetary Science to the NASA Chief Scientist. And I've worked at several centers. I've also been involved in working with human exploration as we trained in a neutral buoyancy tank of water on how to do extravehicular activity, EVAs. Also, we have several other instructors. Carrie Harris will be talking this afternoon on astrobiology. And she is a PhD candidate at Dartmouth and just a fantastic new young astrobiologist and is so knowledgeable. I know you will enjoy her. So what are we going to do today? Well, this is an introduction to astrobiology. We're going to talk about what that means. What is the scope of astrobiology? How interdisciplinary it is. And then we're going to talk about what is life, the ingredients for life. What do we need to make life happen, and how do we define life? But life can't exist any old place. It has to exist in an area that has to be inhabited or habitable. And so we have to define what a habitable region is. And this is really important as we look out into the solar system and look at exoplanets to determine if this exoplanet could be habitable or that one, and why the difference. And then we'll talk about where we are in searching for life and some of the new ideas and tools that have come up in how to really get an idea of, is there life out there? So let's get started. Astrobiology is the study of life in the universe. It really seeks answers to some fundamental questions. You know, these big questions like where did we come from and how did life originate on Earth have been pursued by many fantastic scientists. I want to know, is the Earth unique? Is there places that are Earth-like? We find places that are the size of the Earth, but are they really like the Earth? And did life originate on other planets like Mars or in the moons of Jupiter or other large gas giants? So we're going to find out what are the chances for life beyond Earth. And we'll do this in a mathematical way, but we'll do it in a way that tells you that these are the parameters we have to know about before we can actually do a probability and really get an understanding of life beyond Earth. Well, let's start by a definition. So life is chemistry with a history and memory, so to speak. You know, that's one way to look at it. Another way is life is a self-sustaining chemical system capable of Darwinian evolution. That's kind of the NASA definition, but in reality, that breaks down to these three attributes. Life metabolizes, that means it brings in food. You also bring in a liquid, which in our case is water. That actually is a solvent, extracts energy from the food, and then is used to eliminate waste. So that metabolic process is really important for us. And we have two other attributes that are extremely important. Life has to reproduce and life has to evolve over time. So if we find anything in the universe that has these three attributes, metabolizes, reproduces, and evolves, we're going to call it life. Now for us, what we call Terran life, we use water as a solvent. And it's built from cells. You know, our cells have become quite specialized. We call ourselves complex life because our cells can perform many different functions. We have kidney cells and liver cells and heart cells. And the more specialized our cells become, the more complex we are as humans. And therefore, we are complex life. However, if we find life in the solar system, perhaps it's only microbial life. That will still be fantastic because cells, of course, or microbial life is an important element of building up life as complex as we are. So we're going to explore chemical gradients, things that change rapidly, may be the right environments where life can exist. And we're going to use a 2-bipolymer structure where nucleic acids are used to perform most genetic functions and proteins to perform most catalytic functions. That's what our body does. And so these are really important attributes. Oh, let me go in the right direction. There we are. Ingredients for life. I've talked already about the importance for water. This is H2O. But of course, we have to have the right organic material. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. You know, carbon, hydrogen, nitrogen, and oxygen and phosphorus, these are elements of our DNA. So not only do we have that in our bodies, but we have to consume it. That material is used to repair our cells, to create new specialized cells, and for us to continue to live. We also need energy. You know, it takes energy to make chemical reactions, and the environment that we're in is so important. So it's all about finding the right environment, the habitability, the right energy. And then it takes time for life to be able to grow from inorganic material, organic environment, in the right environment like that, such that we then have cells and then complex cells. Okay, so are we searching for life? Yes, we are, and we're doing it in a number of ways. NASA has these approaches, and so let's talk very quickly about them. Well, we want to talk about how complex life can be, and we do that with what we call the ladder of life. And for looking for regions outside the Earth where life might be, we're going to follow the water. We're going to go to places where water is, because that's one thing we know that we as life here on Earth needs. Maybe that's the same situation in another area. But it's important to note that not all life may be carbon-based. And that's what we call weird life. Also, the size of complex organic material. As life lives and generates organic material, if it can get really big, these complex organic molecules, and once they get really big, they can't be assembled in random fashion. So if we can find an area of complex organic molecules that are really big, that is an indication that life made them and that they are not made randomly. And so also, we're looking for life through how it emits methane and other gases. For instance, methane is an important, what we call trace gas. All life on Earth is involved in a methane cycle. It's part of the metabolism. And then, if we're really looking for complex life, we want to look at technosignatures. And these are signatures that we'll talk about in one organization, SETI, the Search for Extraterrestrial Intelligence, is really all about technosignatures. Okay, the ladder of life, as I mentioned, is a complex series of building blocks, starting with these beautiful bipolar components, working up to more complex environments, and then finally it gets up to this complex life that we would use with metabolism, reproduction, and evolution. Now, the basic importance of our life is right here. This is DNA, and you see that the DNA is coded. This is a helical structure. It's extremely important for us. It has these red, blue, tan, and white elements and other colors. These colors represent certain chemicals, and these chemicals are carbon, hydrogen, oxygen, nitrogen, and phosphorus. Those are all these beautiful chemicals that make up our DNA. Our DNA is in every cell, and this DNA tells us a lot about how we will function, what the color of our eyes are, our hair, all the attributes of our body is encoded in the DNA. Now, DNA in this structure was found in the 1950s, so it hasn't been long that we've really had an opportunity to study this fantastic helical structure and understand what this DNA does to our cells and how it might actually tell us about how susceptible we are for certain diseases. So the search for life really starts next, now that we know what life is, with finding a habitat, finding an area where life might exist in what we call a habitable zone. So what happened on Earth may actually happen on many other planets. So let's look at our solar system, and we need to have a habitable zone, a habitable environment around our sun. It's shown here. This habitable zone allows liquid water to stay on the surface of a planet. Now, it turns out Venus is way too hot. It is too close to the sun. It was in the habitable zone at one time, but it's no longer in the habitable zone, and we believe there's no life on the surface of Venus. Mars is awful cold, and as you can see here, the beautiful planets. Here's the Earth. You can see such tremendous difference between Earth and Venus. Earth and Venus are actually the same size or nearly so, but in reality, the evolution of our planets are so different. And the reason why is because the distance to the sun. The sun heats up over time, has really changed the climate on Venus. Venus, we believed, looked like Earth at one time with all kinds of water and oceans, but now it unfortunately is too hot. The oceans have boiled away, and indeed that means it has a runaway greenhouse going on. The carbon dioxide is 95% of the atmosphere of Venus, and so consequently it is really hot on the surface, hot enough actually to melt lead. Whereas Earth is the beautiful blue planet. Now Mars, we also believe, had wonderful greenhouse gases early on and was a blue planet, but it suffered another problem, and that problem indeed was really the problem of being too small. It lost its magnetic field. It couldn't hang on to that magnetic field, and therefore it began to evaporate its oceans, and then the solar wind took the rest of the atmosphere away. So the solar wind is just beating the heck out of the upper atmosphere of Mars. Now here is the habitable zone of our planetary system over time. And here we are at 1 billion years. And as you can see, Earth is nicely placed. It will be nicely placed in the habitable zone for at least another 500 million, maybe 800 million years. But then we're going to be getting hot like Venus. So what's happened on Venus, it can happen on Earth. There's also a region beyond Mars. It's called the snow line. You know, remember, water is so very important for us. What is water like in the outer part of the solar system? Well, it's so cold beyond the snow line, planetary scientists thought that water would be frozen. But we're finding out that's not the case, because in the outer part of the solar system, we see these moons, and these moons are ocean worlds. You know, like Earth, we have water on our surface, but an ocean moon actually has water underneath it, the ice cap or the ice layer that goes around the moon, like Europa at Jupiter or Enceladus around Saturn. We also find another fantastic planet that has liquid on its surface. That's what these dark areas are on the moon Titan, which orbits Saturn. And that particular moon has not liquid water, because it's way too cold out there, but it has liquid methane. And so consequently, the outer solar system can indeed have some tremendous opportunities for us to search for life. Well, one of the big questions is, are we alone? And this dates back to, you know, we've been thinking about it for hundreds, if not thousands of years. And here is Lucretius, 1st century BC, who said, in the universe, nothing is the only of its kind. In the other regions, surely there must be other earths, other men, and other beasts of burden. And of course, here is an opportunity to look outside of the Earth's bounds and really take a look at the universe. So as you can see, this beautiful blue globe, 75% of it or so is made of water. It's going through its own evolution. The climate on this planet has nothing but changed over time. Here you see the Earth without its clouds, which is just allowing us to look at the ocean and the land versions of this beautiful planet. Well, where are the chances of intelligent life existing beyond Earth? Well, one way to figure it out is through mathematics, and developed by Frank Drake in the 60s. He wrote down an equation. He calls it, and we all call it, the Drake equation. And it's an equation that allows us to really look at various important elements of life. All right. So here is the equation. We'll talk very briefly about it. N is the number of intelligent civilizations out there. You have to know, well, how many stars are there? How many planets are there? Out of the planets, how many habitable worlds are there? And if those habitable worlds have life, what is the indication? And complex life means there has to be some intelligence, some technology going on, and it has to last for a certain length of time. So this is all part of the Drake equation, and it focuses our attention on making observations in each and every one of these areas. So astronomers have to really look at the stars, find the planets, and then planetary scientists get involved in working with them on determining if they may or may not be habitable. As you can see, the astrobiologists are really excited about everything that has to deal with planets and habitable worlds and life. And then SETI, which is the search for extraterrestrial intelligence, it's looking at the latter part, the intelligence, the technologies, and the durations. Okay, let's get to the right slide here. There we go. Well, there's three methods to search for life in the universe. One is our in situ rover called Curiosity, or Perseverance. Both these rovers are on the surface of Mars and are doing fantastic jobs. We actually have a model of it here somewhere. If Cam, you can bring them.
Yeah, 1 second. I'm looking for it. Apologies. I lost it for a moment.
All right. Well, there we go. Yes. So we're going to size it such that it's the same size that it needs to be.
Yeah.
Yeah. So let's see. Here it is. Okay. Size-wise, here we go. There. This is about the right size. As I look, I can see right into the cameras. Now, this has an arm, and it actually can do a number of fantastic things. It actually pulverizes the soil, and then it brings that soil in and puts it in the top deck. That does an analysis, and it tells us what the composition is. What we're finding out is on Mars, there's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all the stuff that we talk about that we need here for life that is part of our bodies. And this rover is confirming that those elements exist on the surface of Mars. It's really a fantastic rover. Now, the reason why some of the pictures from Mars are so spectacular is because of these two cameras right here. They're just pretty close to eye level. And so they give us a stereo view, and it allows us to look out and see some spectacular things. Now, Curiosity has like 17 cameras. So there's cameras down below. So here's cameras right here. They look ahead. We have cameras that look behind. We have cameras that look to the side. And we have a mast that can turn and get a complete view. This actually enables us to really look at the surface of Mars in 3 dimensions. And later on in this lecture, we're going to go to Mars, and we're going to be standing on Mars just exactly as Curiosity has seen it. So I'll let that go for now, and we'll go back to my explanations. Also, remote sensing, like the Webb telescope, is doing fantastic, looking for areas of the solar system where planets have atmospheres that we want to look at the chemistry of those and determine if they're Earth-like or not. SETI has these radio telescopes, and they're doing a fabulous job looking for radio waves that intelligent life might actually have generated. Well, once again, here's our solar system, and the interior planets we talked about may have life. The exterior planets have moons that may have life. But what about the other stars? Well, we have all kinds of candidates. Here's some examples of planets, and they range in all kinds of sizes. When we look out and see the stars in our local neighborhood, here's about 30 stars in our local neighborhood, out to about 12 light years. What you see is they're arrayed all over the place. These are the stars that were generated in the same cloud that we were generated in, with Alpha Centauri and Proxima Centauri being the closest stars. And they have a beautiful planet there. We don't know much about that planet. It may look like this large one or the one over there or that one. These are all artist conceptions. We need to know more about the planets. We can figure out their size, and we can figure out how they go around their stars, but we can't really figure out if they have clouds. So once again, these are artist conceptions, but it gives you an idea that we can see a range of sizes in really important ways. So what about SETI? Well, SETI actually looks out into the galaxy. And here's our galaxy. Our galaxy is 100,000 light years wide. And you can see it's a barred spiral. It has these spiral arms, but then they connect to what is a bar. This is why we call it a barred spiral. And here's our sun. And our sun is, as you can see, quite a distance away from the center and a little distance away from the edge. So we're right in the middle of another spiral arm. Right now, the estimate is our Milky Way has 40 billion stars. Now that means when we think about exoplanets, and we believe there are at least as many exoplanets as there are stars, but once again, not all of them are habitable. The result is, once we look at the Drake equation and everything else that we've been looking at, there may be as many as 10 to 60 billion candidate habitable planets in the Milky Way. So this is just a phenomenally large number. So that means we need to still keep looking, because we think we can find these beautiful planets. Well, let's take a closer look at our own planetary environment. Let's look at our terrestrial planets, the one in particular, Mars, and then we'll look at some of the ocean worlds. So this is Mars. We'll get to it in a minute, but right now let's talk about the search for life with Europa. Here's Europa. Europa is this beautiful moon that has an ice shell. It's cracked so that you can see these cracks, these big cracks. And that tells us the water underneath the ocean is coming to the surface, slashing down on the cold planet and covering up all the craters that we expect would happen there. Now, should we see something on the surface? Well, like these penguins here, we see it in our own ice cap, and the answer is no, we're not going to see that. It's clear that because Europa has really not much of an atmosphere at all, that the life is going to exist in these cracks and below into the water itself. And so here's our concepts as to what's going on. We have this beautiful rocky interior, and on top of that rocky interior is liquid water. We know that from our spacecraft that have flown by it, orbited Jupiter over and over, and really gotten a feel for currents that are running in this water. Therefore, we know that it's liquid, and we know it's water because that's what the top shell is. It's all ice and other chemicals In fact, we think those chemicals would include phosphorus and sulfur for sure. We know it includes that. So Europa may have all the right elements. Remember that carbon, hydrogen, oxygen, nitrogen, phosphorus and sulfur. Europa may have all those things. This ocean, however, can be really deep. We believe it's at least 100 kilometers deep. Well, why do we think that these ocean worlds could harbor life? Well, because when we go to our sub-ice areas, you know, like Antarctica, where there's ice that extends over into the ocean and interfaces with the water, as shown in this upper middle panel, we find it's absolutely teeming with life. You see these things in the upper right? Those are things that are hugging the underside of the ice, suspended in water. This beautiful life occurs. It doesn't need the sunlight. It actually is heated by hydrothermal vents, as we see in these lower panels, the right in the middle and the lower panel. That's a hydrothermal vent. And where we go in our own ocean and see these hydrothermal vents, they're just teeming with life. So this is really a fabulous set of observations. And of course, now we can talk about our nearest neighbor, Mars. So what we see here on Mars is this beautiful planet. It's spinning. There are clouds on Mars, not very many. So we really get to take a good look at its surface feature. Now we're looking at the southern hemisphere. Here is the South Polar Cap. So this tells me, since this polar cap only is seen in the southern hemisphere during the winter, that this is a southern hemisphere winter. That's why the atmosphere, which is made up of carbon dioxide, has snowed out. And so we have a nice little small polar cap. It actually isn't that small. It's probably at least 1,000 kilometers in size. Now you see these really big impacts. Here's Hellas Basin. The Hellas Basin is this huge impact crater. It's a big hole in the crust of Mars. And right there is where most of the dust storms start. The global dust storms love to start right there at Hellas Basin. Yet now, as you look around, you can also see some really spectacular craters. Here's many other craters. And then this tells us that the atmosphere is now thin enough that these objects go through, impact the surface, and there's not enough weathering to eliminate the craters. Now, what's interesting about these is this happens on Earth too. The difference being the atmosphere, the ocean, the plate tectonics on Earth, all those contribute to eliminating the cratering that you see here. Now, when we get down on the surface, as shown in the slides here, we see this beautiful delta. So here, water has come and spewed into this area, dropping its material that it's carried from upstream, creating this beautiful delta. If we were to drain the Gulf of Mexico and stop the Mississippi, this is what it would look like in the United States in the area of New Orleans. It would look like a beautiful delta. Now on the right is a beautiful set of observations where we've detected what we think is hydrogen, which is subsurface indicator of a subsurface water. And that's where all this blue area is, blue in the northern hemisphere and blue in the southern hemisphere. So the water on Mars, it used to be a blue planet, mostly is gone, but there's an enormous amount of water trapped in the crust. And this tells us where that is. And if that's the case, that crust, if the water is close to the surface, would be also frozen. And what we'll see is in these low temperature environments here on Earth, when we go out and look for, well, this looks like Mars, what do we see here on Earth? That's called an analog. So when we go around the Earth looking at different locations and we see opportunities to tell us that these are analogs, we then take a look at them and we determine they're just teeming with life. So life seems to be all over the place on Mars. Sorry, on Earth. Wherever there's water, there's life. But what about Mars? Well, we don't know yet. We're still looking. Well, that gives you a little overview as to what's going on in astrobiology. The rest of the course delves into much deeper, a better understanding of what we're finding in the universe. So this morning we had an introduction to astrobiology. We talked about the ingredients for life. We had talked about where we can go to find habitable environments, and then a little bit about where we are in searching for life. So the rest of the lectures in this series, the next one would be life on Earth over time. How did we get life? What has life been like on Earth? Has it always been here or not? This tells us all kinds of important things about the evolution of life on Earth. That will be important to understand the evolution of life on another planet when we look at it. So the search for life on Mars is the class after that. This goes into depth on many more features we see on Mars. Ocean worlds. Once again, there's so much to learn below the ocean of these, in the ocean of these moons of Jupiter and Saturn, below their icy crust. And we're finding out all kinds of stuff. And then finally, we will end this series with the search for exoplanets, in particular for not just Earth-sized exoplanets, but where are we in terms of finding exoplanets that are Earth-like, okay? Well, I want to thank everyone for coming, but now let's get into the question and answer period. But how we're going to do that is not here in our beautiful lecture dome where we're orbiting Earth, but let's go into, let's beam down to Mars and walk around the real surface of Mars. So if everyone just hangs tight, we're going to reload the dome, and that's going to enable us to be beamed down to Mars. So Cam, Carrie.
Yep, there we go.
Got it. All right, super. Welcome, welcome, welcome. This is the real surface of Mars. This is taken by Curiosity. Let me come up here with you, Cam. There's Curiosity.
Resize.
Yep. There we go. So this little rover has gone through this particular area. That looks good. And here we are in what we call Gale Crater. Now, what's really fantastic about Gale Crater is we see many features that we want to point out. The first one is this huge mountain in front of us. You know, see where I'm pointing? This is Gale Crater, and that's the central peak. It's called Mount Sharp. Right now, Curiosity is halfway up the mountain. That dark area that's between us and the mountain, that turns out to be sand dunes. You know, so the dust has accumulated at the base of the mountain. So what you're seeing is the real structure of the surface. This particular area has been underwater for long periods of time. And it has silted out and created these layered structures. So this is just a beautiful area to explore in greater detail. So do you have any questions about astrobiology and Mars and what we're doing, looking for life in the universe? Please, guys, please
feel free to unmute yourself.
Also, if you can get a group picture, that'd be great. But this is a fantastic environment, Camilo.
Yeah, I'm glad you like it, guys.
I love it, absolutely love it.
Yeah, this comes from JPL. This comes from Parker Abercrombie.
Yeah.
Who just
so if you guys have any
this.
questions, just like feel free to ask them. Sorry, Jim, I interrupted you.
No, that's fine. Yep.
Some people have actually walked away to see that little mountain.
I noticed everybody's just gone and started exploring all everywhere.
Everybody left.
Yeah,
that's true.
Look, there's people there. You can see the speck of them.
People are on their own missions here.
Yeah, they're on their own missions. You're right. You're exactly right.
I'm gonna put some nice landers here. I know this is not biking site, but it's just for fun.
Yeah.
It's like this size.
It's a little. Yeah, actually, you're right. That is about the right size. Oh, Miriam, I'm sorry. I was talking while you were talking. Go ahead.
I was just trying to go after some people, and I see one of the attendees has just gone extremely west, and one is trying to get on the mountain.
Oh yes, I see someone over there.
Yeah.
Now this is a crater. This is the central peak in the crater, and the crater wall is right here. And on the other side of the wall used to be the ancient ocean of Mars. And so the water is poured over this crater wall, and the water has come down and filled this crater. So this crater had a huge amount of water for probably several hundred million years. This is the Viking lander. It's as Camilo said, it's not one that actually is in this area, but it is sitting on Mars. It was our first life detection mission, and it didn't find life, but it didn't know what it was looking for either. So that was it. I think I would say that this mission just was too early in its approach to looking for life. This is the little Sojourner.
I have
the little
someone.
And filled this crater. So this crater had a huge.
Yeah, there you go.
Yeah. So here, this is Sojourner. This is our first successful lander on Mars. So you can see it's just about the size of a microwave oven. Okay. I mean, it's not very big. And it had a little arm. That then would touch a rock, and we would get information about that rock and understand its mineralogy.
You can raise Sojourner if you want.
No, that's fine. It looks great sitting there.
Okay.
Yep. Any questions?
Gene, maybe you can tell the audience why Mars became like this. What happened with the atmosphere that all the water disappeared?
Well, we do know that something happened to Mars for which the water cycle, where you have an ocean, it evaporates, it transports in the atmosphere, and then it rains, and then goes back into the ocean. That's the water cycle. That water cycle got disrupted. And once it gets disrupted, you start losing water. So what happens is it evaporates, but then the sun breaks apart the hydrogen and the oxygen. The oxygen goes to the upper atmosphere, and then the solar wind strips it. Now, the solar wind is stripping it because it no longer has magnetic field. It lost its magnetic field. Now, once it loses its magnetic field, then the solar wind has an opportunity to really just get really close to the upper atmosphere, and the whole dynamics of the atmosphere interaction with the solar wind changes, and therefore you start stripping key things like the oxygen away. And then once you strip the oxygen away, the hydrogen doesn't have an opportunity to recombine and create the water again. So over time, and this took several billion years, Mars's water cycle really ended up going from liquid to vapor, and then solar wind stripping it and not coming back. And now it's an arid, dry surface. But we do know that there's a lot of water underneath the surface. It's trapped underneath the surface as ice. And it's not very far below us.
Jim, one question is possible that at some point in history that can happen to Earth?
Yes, indeed. We think as the Earth heats up over time because of not only the sun, but indeed the solar input changes over time and gets much hotter. That climate change is also due to humans. Then the dynamics will change, and eventually, if we lose our magnetic field, then we know the process of the solar wind stripping. All right, we have a couple questions. Go ahead.
Heather, go.
What's the gravity like on Mars compared to Earth?
Yeah, the gravity is less. So you wouldn't be walking around like we do so nicely. You'd actually be hopping a little bit. It's about 40% that of the Earth. All right?
About 40% of the Earth.
Yeah, so if you were 100 kilograms, you'd weigh 40 kilograms on Mars.
Perfect. Anybody else? Otherwise, let's quickly get a screenshot and let Jim rest, because it's 4 o'clock in the morning for Jim. Oh no, it's better now, I think. Actually.
No, it's better. Yeah, no, we're good. We're good. Yeah, come on.
How long do you think that it will take Mars to become habitable as Earth?
Good question. Well, the sun, this is a really good question, because we know the sun will heat up. It will heat the atmosphere. That means the polar cap will start to melt. Hopefully, the rest of the planet will get warmer, and Mars might end up becoming habitable for a little period of time in the future. It probably is going to occur in the next 800 million years. So it takes a while. But Mars will change significantly. Climate on Mars is changing, just like climate on Earth changes.
Jim, can I ask you something? So, for example,
sure.
Elon Musk a few years ago said that let's nuke Mars. Is it possible that launching a nuclear bomb on Mars could change its environment and making it habitable? I know it might sound like a crazy idea, but some people were talking about it on the internet. So maybe you can tell us about
sure. Yeah, the idea comes from the concept of trying to melt the North Polar Cap. Now, unlike the South Polar Cap, which is completely CO2, the North Polar Cap has a significant amount of water, H2O, frozen water, with a veneer of CO2 on top of it. So that frozen water is been piled up. It's about 1/7 of the ancient ocean. So the idea is, how can we melt that polar cap? Well, we're going to literally let climate change do that. There's no reason to nuke it. We don't think nuking the polar cap will bring back the water on the planet. what it will do is dump a lot of radioactive material everywhere on the planet, meaning that humans won't be able to come to the planet for a while, particularly in those areas in the Northern Hemisphere where the nuclear explosions would be planned to take place. But once again, the idea is really all about how do we melt the polar cap, but doing it with nuclear bombs is not the way to go.
Great answer. Thank you, Jim.
Could we get everybody lined up for one picture? Just because we've got to.
Sure, absolutely.
Yeah. Okay.
All right. How about let's come down here around the rover, and then you can take a shot at us. Okay.
Fantastic.
So let's go down here. Yeah, here we are.
Can everyone please face the avatar that's called Adam, where I'm talking from here? I can take a picture from us, can stand in between the rover as a group.
Fantastic. So if everybody faces us here, great. All right.
Facing Isha?
Yeah.
Ah, okay, good. Here we go.
I meant facing Adam, but let me just change it for my avatar. Hang on.
There we go. Perfect. This is great. Bisma, if you can move slightly into this, that's it. There we go. Isha, you can get in as well if you like. There we go. All right.
1 second, let me just move.
Cool. All right. And we'll get a close up.
See you get in the photo as well and turn around.
All right.
Who are we looking at?
Looking at
Okay.
Isha.
Cheese.
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 You get us?
Yeah, we're done. Thank you all. Thank you very much.
Lovely.
Fantastic. Thank you again.
See you in the evening.
Yes, for all of you who's watching, the ISS lecture is going to be fantastic. Hope you'll watch out. We'll be setting up the stream soon. See you tonight.
Wait, when is the next lecture?
Yep, today
In 5 hours.
In 5 hours from now, yeah.
Oh, okay. Thank you.
Pleasure.
All
Yeah.
right, guys. Well done.
Wasim, do you want me to